I am pleased to introduce Professor Ismail Sahul Hamid, who is an associate professor in the Madurai College, Madurai, Tamil Nadu in India. And we want to talk about domination and coloring related concepts in graphs. Professor Hamid.
Yeah, yes, sir. I'm here.
Please, okay.
Yeah.
Thank you so
Very
much
nice.
for accepting the invitation. Thank you.
Thank you so much, sir. It's nice meeting you all. First of all, let me congratulate your team for having taken the very good initiatives, which is the need of the hour. Really, it's very rare in this case, organization of this kind of workshops to the research scholars, really very purposeful to them. So first, my congratulations to you and Hamid, who is the person keeps me interacting the past 20 days. And then thank you for the nice opportunity for me to share some of my ideas to share with the young researchers. I understand that most of the participants are basically research scholars. Let me go a little slower and discuss the fundamental concepts. And my objective is to motivate the research scholars to how to initiate the research, how to go ahead further and further. So I understand now from my region, most of the scholars are struggling with how to proceed with a problem is given to them. So they are stuck with a problem. So this problem may be universe. So if these things in mind, I would like to go slower and just initiate the study. What is happening? So basically I would like to present my work that we have done for the last 5 years. Let me share the screen first. So the screen is visible, sir?
Yes, everything is okay. Yes.
Yeah. Thank you. So the topic of my talk is today is the domination and coloring related concepts. So all the speakers, professors are talking about domination. Of course, the theme of the workshop is also on domination. Now, the reason that 20 years, a new trend in research is going on, which connects the two major concepts in graph theory, namely domination and coloring. So several concepts are being emerged by interrelating these two major concepts, domination and coloring. So in order to get into the topic, I would like to recall the fundamental terms, namely domination and coloring to the audience. First of all, domination. So by a dominating set, we mean a set with the property that every vertex outside the set has a neighbor in the set. For example, if S is a set, which is said to be a dominating set, for every vertex U outside the set S, there should be a vertex V in S, such that they are adjacent. If the property is satisfied by the set S, then we call S as a dominating set. Of course, the whole vertex set is a dominating set, and therefore it is quite natural and reasonable to look for the minimum cardinality of a dominating set, and this is called domination number, which is denoted by comma of G. So comma of G is domination number, which is defined to be the minimum number of vertices in a set with a property that every vertex outside the set has a neighbor in S. For example, consider this graph. See this, for this graph, domination number is 1 because this vertex, center vertex, will take care of the domination. So this vertex will dominate all the other vertices. Therefore, gamma is equal to 1 here. And for this graph, see there are two triangles where the corresponding vertices are adjacent here. So here, one vertex inside the triangle, the one vertex outside will take care. Therefore, the gamma of this graph is 2. Right. And coloring, all of us know, coloring of a graph is an assignment of colors to the vertices with the property that adjacent vertices should be given different colors. So assignment of different colors to different vertices. For example, if there are 10 vertices in the graph, assign 10 colors to 10 vertices. So that is called a trivial coloring. So obviously it's a coloring, it's called a trivial coloring. And therefore it is quite natural to look for the minimum number of colors in a for a coloring to a graph, which is called the chromatic number and is denoted by chi-object. I recall, so dominating set is a set with the property that every vertex outside the set has a neighbor in S. Coloring means assignment of colors to the vertices such that adjacent vertices are given different colors. So what is the minimum number of colors required for a coloring, which is called the chromatic number? For example, these two graphs are three colorable. See, a three coloring for each of these two graphs are given. Therefore, the graphs are having chromatic number 3. Suppose a K coloring is given for a graph G. K coloring means a coloring which uses K colors. You collect all the vertices that receive the color I and name it as the set Vi. Then these sets Vi will have the following properties. Definitely the set is independent, right? Because no two of them are adjacent, because if they are adjacent, they should be given different color. Therefore, Vi must be independent set and they are mutually disjoint. A vertex cannot be in two sets because a vertex is given exactly one color. So they are mutually disjoint. So if you collect all the sets Vi, it will be equal to V of G. Therefore, if Vi is the set of vertices receiving the color I, then they are independent and they are mutually disjoint. Their union equals the whole vertex, which means the collection of the sets V1, V2, etc., Vk forms a partition of V of G into independent sets simply. Thus, a K coloring gives rise to a partition of V of G into K independent sets. So a coloring can also be regarded as a partition of the vertex set into independent sets. Such a partition is called a chromatic partition. So a K coloring can also be called as a chromatic partition. And these sets V1, V2, etc., Vk of this chromatic partition are usually called color classes of the graph. So with this terminology, chromatic number can be defined as the minimum order of a chromatic partition. By order of the partition, I mean number of sets. For example, order of the partition V1, V2, Vk is K. So what is the minimum order of a chromatic partition? That is the chromatic number. So this is another interpretation for the coloring. So for example, consider this graph. A 3 coloring is given. So this is a chromatic partition. I collect the red colored vertices. That's the first color class. And the yellow color is the second color class. And the rest is the third color class. So this is a chromatic partition of the graph. So chromatic partition means a partition of the vertex set into independent sets. That's what's a color. So now recent years, several parameters are coming up by imposing conditions on the color classes on of the chromatic partition. For example, if you demand at least one color class of a chromatic partition must be a dominating set, then that is called a dominating Chi coloring, like that. In fact, that is the result. There is a Chi coloring which is always a dominating Chi coloring, which means there is always possible to find out a Chi coloring where at least one color class will be a dominating set. And several parameters have been defined or emerged by imposing suitable conditions or interesting conditions on the color classes. For example, B coloring was introduced by Irving et al. In the year 1999. This is a kind of concept which is interrelated, relating the concepts of domination of the coloring, which means specifically which will impose certain conditions on the color classes. And fall coloring by the year 2000 by Dunbar, and dominator coloring, very interesting parameter, introduced by Guerra in the year 2006. And dominating Chi coloring was introduced by us with my professor Armugam and myself in the year 2007. And global dominating Chi coloring is by myself and my student, and dominated coloring in the year 2015. In this sequence, we recently defined the concepts of global dominator coloring and the gamma coloring. So today I would like to concentrate on these two concepts, namely global dominator coloring and gamma coloring. So let us first focus on gamma coloring. So what is a gamma coloring? So in order to get an idea about the gamma coloring, it would be better if I can define what is a dominator coloring, because which is the motivation actually for us to define the concept of gamma coloring. So what is a dominating coloring? Okay, suppose a coloring is given for a graph G. So assume that a coloring is given to a graph G. Consider a vertex V, and I say that V dominates a color class of the given coloring. I say V dominates a color class of the given coloring when, if either singleton V is a color class or there is a color class V1 in the coloring with the property that V is adjacent to all the vertices of the coloring color class V1. So for a given coloring, a vertex V is said to dominate a color class either singleton V itself is a color class or V is adjacent to all the vertices in at least one color class of the given coloring. In this case, I say that V dominates a color class. So Guerra demanded that every vertex must dominate a color class. Every vertex must dominate a color class. So given coloring, and Guerra demands the coloring to satisfy the property that every vertex of the graph must dominate a color class. So such a coloring was called dominator coloring. So dominator coloring is a coloring basically with the property that every vertex must dominate a color class. For example, consider the trivial coloring, which means you assign different colors to different vertices. Suppose there are 6 vertices, assign 6 colors to 6 vertices. So certainly every vertex will form a color class, and therefore every vertex will dominate itself, and therefore the trivial coloring is always a dominator coloring. So existence is guaranteed because a trivial coloring is a dominator coloring, and therefore we look for the minimum number of colors required for a dominator coloring, and this is called dominator chromatic number, which is denoted by chi d of G. So chi d means dominator chromatic number, which is defined to be the minimum number of colors required to color the vertices such a way that every vertex dominates a color class. Let us see some examples which will give you a better idea about the concept of dominator coloring. For example, this is a bistar or double star. Certainly, the chromatic number for this graph is 2. See, red color and green color. Will it be a dominator coloring? See, for example, V4, consider this vertex V4. Consider this vertex V4. This V4 dominates the red color class, right? This vertex V4 is adjacent to all the vertices receiving the color red. Therefore, V4 dominates the red color class. Okay, therefore, the vertex V4 is satisfying the required condition. What about V5? Yeah, V5 is also satisfying because V5 dominates the green color class, right? What about the other vertices, that is pendant vertices? Does V1 satisfy the condition? The V1 is adjacent only to the vertex V4, which is given green, but some other vertices are also receiving color green, to which V1 is not adjacent. Therefore, V1 does not dominate. V2 also does not dominate. So in fact, none of the pendant vertices dominate a color class. So only V4 and V5, each of them dominates a color class, and therefore this is a coloring but not a dominator coloring. What about this coloring for the same graph? So I give additional color, blue, in addition to green and red, I give additional one color. Certainly see, V4 dominates itself because it's a singleton color class. V5 dominates itself. What about V1? V1 dominates the green color class, right? Right? V2, V3. Each of V1, V2, V3 dominates the color class green. And each of V6, V7, V8 dominates the color class V5. Therefore, every vertex satisfies the required condition demanded by a Guerra, and therefore this is a dominator coloring. And in fact, with the 2 colors, this is the only 2 coloring for the same graph, which is not satisfying the condition for dominator coloring, and therefore a dominator coloring for this graph requires minimum 3 colors. We could manage with 3 colors, and therefore chi d is exactly 3. So chi for the graph is 2, but Chi-D is 3 for this graph. So this is the dominator chromatic number. So what is gamma coloring? So in what way dominator coloring is related with gamma coloring, or how dominator coloring motivates us to come up with the new concept of gamma coloring? Let us see. Right. You consider a Chi-D coloring. By Chi-D coloring, I mean a minimum dominator coloring, right? A minimum dominator coloring. That's what Chi-D coloring. So consider a Chi-D coloring V1, V2, etc. V Chi-D. So there are Chi-D color classes V1, V2, etc. V Chi-D. Okay, choose one vertex from each color class. Choose one vertex from each color class and name them as V1, V2, and so on, V Chi-D, and put all these vertices in a set D. So D is the set of those vertices selected from each of the color classes in the Chi-D color. No, I would like to prove that D is a dominating set. So dominating set. So what is D? So this is what D. So how to prove D is a dominating set? To consider a vertex V outside the set and find a neighbor in the set D. How to find the neighbor? So by definition of Chi-D coloring, every vertex must dominate a color class. So in particular, this vertex V also must dominate a color class. Suppose this vertex dominates this color class, for example, this color class, which means V must be adjacent to every vertex in the color class. So in particular, V will be adjacent to the vertex, this vertex also, which has been chosen for the set D, and therefore the vertex V finds a neighbor in the set D, and therefore D becomes a dominating set, right? But you see what a beautiful property this dominating set D has. See, this is a dominating set where all the vertices receive different colors. V1 has color 1, V2 has the color 2, V3 has the color 3. Therefore, the thus constructed dominating set has the beautiful property that all the vertices are receiving different color, right? Therefore, every dominator coloring admits a dominating set where different vertices receive different colors. So if you look at the vertices, or if you look at the dominating set, the dom set would be more colorful. So red, green, because only one red color vertex, only one green color vertex. Therefore, in that way, the dominating would be very beautiful to see. So the set will be so colorful, and therefore I called it as a colorful dominating set. Professor, am I audible? Please kindly confirm. Professor, am I audible?
Yes. Everything.
Thank you. Thank you, sir. Okay. So a dominating set, which is said to be colorful if all the vertices are receiving different colors. So in this terminology, we observe, or the above observation can be stated as every dominator coloring admits a colorful dominating set. So very beautiful property that Guerra proved. Actually, Guerra proved this result for some other aspect, but we have taken the essence of the result. So he proved every dominator coloring admits a colorful dominating set. So we looked at the reverse process. What is it? So suppose a coloring which admits a colorful dom set, will it be a dominator coloring? So Guerra what introduced? Guerra proved that a dominator coloring will admit a colorful dom set. I asked the reverse question. Suppose a coloring admits a colorful dom set, will it be a dominator coloring? That's a question. So this is the very key point behind the introduction of the concept of gamma coloring. But the answer is fortunately no. Fortunately no. For example, you consider this graph. This is a bipartite, and therefore chromatic number is 2. So I colored with 2 colors, red and blue. So see here, this is a colorful dom set. This vertices V1 and V4 form a colorful dom set. This is a dominating set and also colorful. But will it be a dominator coloring? No, because look at this vertex V5. It does not dominate a color class because V5 is adjacent only to V1, which receives red color, but red color is also given to the color, the vertex V3, to which V5 is not adjacent. So V5 does not dominate any color class, and therefore this coloring is not a dominator coloring, but the coloring satisfies the property which was satisfied by a dominator coloring. So what I want to convey, dear friends, that there are colorings that behaves like dominator, but not a dominator coloring, right? So there are colorings which possess the property satisfied by a dominator coloring, but it's not actually dominator coloring. So therefore, in between coloring and dominator coloring, something is there. So there is a scope for studying such kind of coloring, right? Why can't we initiate a study on those concept of coloring? So why can't we study such a coloring, right? So coloring which is not dominator, but behaves like the dominator coloring. So such a coloring we called as a gamma coloring. So please understand. So gamma coloring is basically was motivated by a beautiful property of a dominator coloring, right? So what is the gamma coloring? Gamma coloring is a coloring which admits a colorful dominating set. Very simple. So what about the existence of a gamma coloring? Obviously, see, that's also a beautiful concept. See, whole vertex set is a dominating set, and assignment of single different color classes to different vertices forms a coloring. So if you pool all the color classes, we will get the whole vertex set, which is your dominating set. Therefore, the trivial coloring is obviously a gamma coloring. So trivial coloring is obviously a gamma coloring. Therefore, existence is guaranteed. And therefore, we are looking for the minimum number of colors required for a gamma coloring. And that is called gamma chromatic number, which we denote it by chi gamma. Therefore, now a dominator coloring is a gamma coloring, which means now after introduction of the concept of gamma coloring, dominator coloring becomes a special case of gamma coloring. So dominator coloring becomes an example of a gamma coloring, right? So let us see. See, dear friends, please see how a new concept is being introduced. So this is a thing that actually we need to acquire, right? Let us see some examples. So consider this graph, which is certainly a bipartite graph. Therefore, chi is actually 2, which is not a gamma coloring, because gamma coloring means coloring which should admit a colorful dominating set. See, the gamma is 4. Gamma is 4. But there are only 2 colors. Therefore, we cannot have a dominating set receiving different colors. The dominating set must have at least 4 vertices. If you want that DOM set to be colorful, we need at least 4 colors. Therefore, your 2 coloring cannot be a gamma coloring for this graph. At the same time, you consider this graph, I have added 2 more colors. So I have arrived at a 4 coloring, which is obviously a gamma coloring, because these 4 vertices is a dominating set. Therefore, which is also colorful. So this is a coloring which admits a gamma coloring, which admits a colorful DOM set, and therefore this is a gamma coloring. So the earlier is not, but the later is, right? Fine. You consider the Peterson graph. So this is a coloring. I have given 4 colors, but chromatic number of this coloring graph is 3, but I have given 4. Certainly you can see this is a gamma coloring, because the vertices 1, 2, 4 form a dominating set. 1, 2, 4 form a dominating set, which is colorful because colors are 1, 2, 4. So these 3 vertices form a colorful DOM set. Therefore, this is a coloring admitting a colorful dominating set, and therefore this is a gamma coloring. Therefore, 4 colors are enough to have a gamma coloring. Therefore, chi gamma is less than or equal to 4. But it's actually 4. Why? We cannot manage with the 3 colors. So how to prove 3 colors we cannot manage? Suppose there is a gamma coloring with 3 colors. There is a gamma coloring with 3 colors. which means there is a dominating set which is colorful. Because gamma equal to 3 means gamma equal to 3 for this Peterson graph. Therefore, a set D which is colorful will contain exactly 3 vertices. So a colorful dominating set with 3 colors will be a gamma dominating set. This gamma set, that is minimum dominating set. There is a property for a Peterson graph. A gamma set will be an open neighborhood for some set. We cannot find out a gamma set which is not a open neighborhood of, for example, you consider this set. This is the neighborhood of the vertex, this vertex, right? These 3 vertices forms a dominating set, actually gamma set, which is neighborhood of this vertex. So this is a property the Peterson graph actually has, which means a minimum dominating set for the Peterson graph is nothing but open neighborhood of some vertex. Therefore, if D is a colorful dominating set, this will be a open neighborhood for some vertex. Therefore, this is colorful means this vertex will, these 3 vertices will be given 3 different colors to which this vertex will be adjacent. Therefore, this vertex will be required a new color, namely 4. Therefore, we cannot manage with the 3 colors for a gamma coloring. Therefore, gamma chromatic number for the Peterson graph is actually 4. Okay, bounds on chi gamma. Actually, if there are n vertices, naturally n colors are nf, and therefore chi gamma is at the most n. When the equality will hold only for complete graph or totally disconnected graph. When kn or kn bar only the graphs to which chi gamma required to be n. Okay. And when chi gamma is equal to n minus 1. So we next tried to investigate what are the graphs. Please understand all the graphs that we considered here are connected. There is a convention. So when chi gamma is equal to n minus 1. So chi gamma is equal to n minus 1 if and only if G is obtained from kn minus 1. You consider a kn minus 1. You consider a kn minus 1. You consider a kn minus 1 and add a new vertex here. And you join this vertex to at least one vertex here. At least one vertex here. One or more vertices of kn minus 1. Okay, so this is the graph. This is the only graph to which chi gamma is equal to n minus 1. The proof is really very interesting. As the time is very less, I avoid proving the result. And also we characterized what are the graphs to which chi gamma is equal to 2. So chi gamma is basically ranging from 1 to n. And we characterized those graphs, the extremal graphs. What are the graphs for which equal to chi equal to 1 and chi gamma equal to n? That are settled down. And also we characterized those graphs for which chi gamma equal to n minus 1 and also chi gamma equal to 2. And therefore, now what are the possible values now from 3 to n minus 2? The chi gamma will assume any value in between 3 and n minus 2, which means the bounds are very sharp, right? So given integer n greater than or equal to 5, the parameter chi gamma can assume any value in the interval 3 and n minus 2, any value in between 3 and n minus 2. It's called a type of interpolating type theorem, right? So we constructed some graph to which the chi gamma will be the number. So what is the relationship among the parameters chi gamma, chi and a gamma? So we just now observed that every dominator coloring is a gamma coloring. Both are minimum parameters and therefore obviously chi gamma is less than or equal to chi d, because every dominator coloring will be also a gamma coloring. Therefore, chi d colors are enough to have a gamma coloring and therefore chi gamma is less than or equal to chi d. Obviously, every gamma coloring is basically a coloring. Therefore, chi gamma must be at least chi. So this is a nice setup among the parameters chi gamma and chi d. So chi less than or equal to chi gamma less than or equal to chi d. Right. So which was earlier chi less than or equal to chi d. Now, in between these two, there is a parameter coming inside, in between chi and chi d. So our parameter chi gamma finds its own position very comfortably in between chi and chi d. So which I see a very beautiful result, but elegant, simple but elegant. Right. So now chi less than or equal to chi gamma less than or equal to chi d. For the Peterson graph, so whenever we have a chain of parameters or inequalities of parameters, we will study the what are the graphs for which all the parameters are equal, what are the graphs for which all the parameters are different, when these two are equal, when they two are equal. So there are several problems could be discussed. So for Peterson graph, chi equal to 3, chi gamma just now we proved 4, and chi d can be proved to be 5. See, Peterson graph, for the Peterson graph, all the three parameters are different. All these three parameters are different. And naturally, one may ask, is there any graph for which all the three parameters are equal? Yeah. If you take a graph with full degree vertex, that is a graph having a vertex which is adjacent to all the remaining vertices, to which all the three parameters coincide, or chi equal to chi gamma equal to chi d. So there are graphs for which all the three are different. There are graphs for which all the three are the same. It's very interesting. Okay, that shows the interesting problems, right? Now this is very obvious. You can easily observe gamma less than or equal to chi gamma. So what is chi gamma? Chi gamma means the minimum number of colors we require to have require to have a dominating set with different colors. So suppose there is a chi gamma coloring, V1, V2, etc., V chi gamma. Let me draw the better. Suppose, yeah, we have a coloring V1, V2, V3, and so on, V chi gamma, right? So this is a gamma coloring means there is a dominating set. There is a dominating set which will intersect the color classes at most one vertex, maximum one vertex. It may not intersect the color classes. Even if it intersects all the color classes, so chi gamma, the set D will have at least the D will have maximum. So gamma is less than or equal to the dominating set. Cardinality of dominating set, which is less than or equal to chi gamma, right? So when the cardinality of D will be equal to chi gamma, if D will intersect all the color classes, then cardinality of D equal to chi gamma. Otherwise, it will be strictly less than chi gamma. Therefore, gamma is less than or equal to chi gamma. Right. So chi gamma is bounded below by gamma. In the beginning, I told chi gamma is a parameter which is it is a connection of both gamma and chi. So naturally, there should be a result which connects both gamma and chi. Already chi gamma is bounded below by chi, already observed. Now chi gamma is also bounded below by gamma, right? The another thing is chi gamma is less than or equal to chi plus gamma minus 1. Chi gamma is less than or equal to chi plus gamma minus 1. So this, see, there is a relation of chi gamma, right, with both chi and gamma, chi plus gamma minus 1, right? So how this result is proved? See, you consider a gamma set D. You consider a gamma set D. Therefore, there will be gamma vertices in this set D. There will be gamma vertices. Okay. You assign a chi coloring. Which means there will be chi colors used in the graph. So graph will be like this. Oh, see, this is the outside D. So D bar. In between D and D bar, there will be some edges. Among the vertices of D bar also, there will be vertices. So D is a gamma set. Therefore, it will contain gamma vertices. And you assign chi colors to this graph. Okay. Now I retain one vertex in the set D. I just catch this vertex and erase I remove all the colors of the vertices. I remove the colors of the remaining gamma minus 1 vertices. So remaining gamma minus 1 vertices, I remove the colors already given. Now I assign new color. So already chi colors are given. So for this vertex, I give new color. So chi plus 1th color. Chi plus 1th color. I don't see anything about any property of the graph, nothing. Is it visible? Yes, Hamid.
Yes,
Hamid?
everything is fine.
Sir,
Everything is
visible.
fine. Yes, yes.
Yeah, thank you.
Visible, sir.
Thank you. So we have see how many more colors we have given. Chi minus comma minus 1 more colors have been given naturally. So we have got a dominating set where all the vertices are receiving different colors. Therefore, by just introducing gamma minus 1 more colors, we could have a coloring which admits a dominating set which is colorful, and therefore we can have a gamma coloring with most chi plus gamma minus 1 colors, and therefore chi gamma is less than or equal to chi plus gamma minus 1. Okay, and therefore see, chi gamma is bounded below by both chi and gamma, and therefore chi gamma is at the most maximum of both chi and gamma, and is bounded above by chi plus gamma minus 1. Therefore, you see, chi gamma is beautifully sitting inside two relations which connects both chi and gamma. That's the beauty of the parameter chi gamma that I observe. Okay, fine. And now naturally we can see there is a very routine research. So once upon receiving a relationship among 3 or 4 parameters, then we will see what are the graphs achieving these two and those two. Therefore, what are the graphs with the chi gamma equal to chi? That's what we started investigating. But unfortunately, we could not settle completely the problem. But we could come up with certain class of graphs for which chi gamma equal to chi. For example, all the graphs of order n with the maximum degree n minus 1 or n minus 2. So for those graph, chi gamma equal to chi. And a graph which is P4 free is also satisfying the equation chi gamma equal to chi. That also we proved. And for all these split graphs means, the vertex set can be partitioned into 2 sets, P1 and P2. One is independent, one is complete. So completely different concepts. One is complete, one is independent. That's called a split graph. For those graphs, chi gamma is also equal to chi. So the condition does not alter the coloring. So no color is more color is required than chi in order to have a chi gamma coloring. Therefore, these classes of graphs. But still, dear friends, the problem of characterizing the class of graphs for which chi gamma equal to chi is still open. And chi gamma equal to gamma, yeah, again the same. For the corona of a graph, chi gamma equal to gamma. And for simple, the paths and cycles of order at least 3, both are same. And Q1 is a very nice class of graphs, Q1, hypercubes. For the class of bipartite graphs, for those graphs also chi gamma equal to gamma. So there are classes of graphs for which chi gamma equal to chi, and there are classes of graphs for which chi gamma equal to gamma. But still, the general problem is unsettled. Okay. But even if we could not get a structural characterization of graphs for which chi gamma equal to gamma, but we could have a property characterization of graphs for which chi gamma equal to gamma. Chi gamma equal to gamma only if G has a coloring. G has a coloring with the property that there is a gamma set which intersects each color class of the coloring. Please understand, the coloring not necessarily be a minimum coloring. The coloring not necessarily be a minimum coloring. There is a coloring, but should have the property that there is a gamma coloring which will intersect each color class of the coloring. If it's so, then for which graph chi gamma will be equal to gamma. So that's a beautiful result. But this result will not be useful to see the structure of the graph, but might be useful to get the structural characterization of the graphs for which chi gamma equal to gamma. But we did not proceed further. We do not know the degree of difficulty also. Must be difficult obviously. See, for bipartite graphs, it's very interesting. See, chi gamma was proved to be less than or equal to chi plus gamma minus 1, right? When the graph is bipartite, then chi is equal to 2. Therefore, this number is actually gamma plus 1, right? The upper bound is gamma plus 1. Therefore, chi gamma is less than or equal to gamma plus 1. But already we have seen that chi gamma is at least gamma. So chi gamma lies between gamma and gamma plus 1, which means there are only two possibilities for chi gamma, is either gamma or gamma plus 1. So very interesting observation. So for bipartite graph, chi gamma is either gamma or gamma plus 1. So naturally, what are the bipartite graphs for which chi gamma equal to gamma and chi gamma equal to gamma plus 1? So of course, we could be successful in characterizing those bipartite graphs. Therefore, which means the determination of chi gamma for bipartite is completely settled on in terms of gamma. That is the only negative side, right? Because finding out gamma for bipartite graph is proved to be NP complete, right? Therefore, we could settle chi gamma is gamma for this alone. Chi gamma equal to gamma plus 1 for this alone. That we could be successful. But we do not finding out what are the bipartite graphs for which chi gamma, so determination of gamma for bipartite graphs is very difficult. Therefore, anyhow, partially we could characterize chi gamma for bipartite in terms of gamma. Okay. So then what are the other research has been done on gamma coloring? If you ask, then for unicyclic graph, we could obtain, and for mycelial skin construction, then for some special classes of graphs, and criticality, vertex criticality, edge criticality. So your entire thesis have been spent on gamma coloring. One of my student has submitted awarded the degree which was devoted on gamma coloring. And I would like to just introduce in 5 minutes the another parameter of this kind, namely global dominator coloring. Let me do it in maximum of 5 minutes. Global dominating coloring, right? So for this, I need the definition of global dominating set. Dominating set means a set with a property that every vertex outside this set has a neighbor in S. Global dominating set needs one more condition, which also requires a non-neighbor. So a set S is said to be a global dominating set if for every vertex U outside S, there should be two vertices in S, say V and W, such that one is a neighbor, the other is a non-neighbor to U. So this is a global dominating set. So naturally, by accurately true that the whole vertex set itself is a global dominating set, and therefore we are looking for the minimum cardinality of a global dominating set, that is called a global domination number, which is denoted by comma G. I'm sorry, this is not gamma, this is comma G, global dominating set. Okay. Now for a given coloring, I already defined when a vertex V dominates a color class if it is adjacent to all the vertices of the color class. If the vertex V is not adjacent to any vertex, any of the vertices in a color class, then I say that this color class is an anti-dom color class. So for a given coloring, a color class is said to be a dom color class of a vertex V if V dominates the color class. A color class is said to be anti-dom color class if anti-dom color class of V if V finds no neighbor in the color class. I repeat, a color class is said to be a dom color class for V if V is adjacent to every vertex of the color class. Whereas A color class is said to be an anti-dom color class of V if V has no neighbor in the color class. Okay. So what is a global dominating set? A set with a property that every vertex has a both neighbor as well as a non-neighbor. In that aspect, I define every vertex has a DOM color class, then that is called a dominator coloring. So what was a dominator coloring? Please recall the definition of dominator coloring, which demanded that every vertex must dominate a color class, which means for every vertex, there should be a DOM color class. So now I combine the definition of global domination with dominator coloring to arrive at global dominator coloring, right? So which demands every vertex must have both a DOM color class and anti-DOM color class. Just like the definition of global dominating set, a neighbor and a non-neighbor. Like that, I combine the concept of dominator coloring, or I impose the concept of dominator coloring in the context of global domination and arrive the definition of global dominator coloring. So a global dominator coloring is a coloring with the property that every vertex has both a DOM color class and a anti-DOM color class. Okay, that's called a global dominator coloring. Please, this is a caution here. Singleton V is a DOM color class of V, whereas which is not an anti-DOM color class of V. So there should not be in confusion to the researchers. Obviously, if there is a full degree vertex, that vertex cannot have a anti-DOM color class, because full degree vertex means that will be adjacent to all the vertices in the color class. Therefore, it cannot find an anti-DOM color class. Therefore, when a graph admits a full degree vertex, the graph cannot have a global dominator coloring. So throughout the study, we assume the graph to be a graph with no full degree vertex. Okay, fine. Now let us see one example. For example, again the bi-star for which chi equal to 2, a 2 coloring is given. Certainly, this is not a dominator coloring, because we have observed none of the pendant vertices dominates a color class. So it's a coloring, but this is a dominator coloring. This is a dominator coloring. Observe. Is it a global dominator coloring? What is global dominator coloring? So every vertex must dominate a color class and should have a anti-DOM color class. For example, you consider this vertex. You consider this vertex. For this vertex, this is a DOM color class. This is a DOM color class. So what is an anti-DOM color class? V2 is an anti-DOM color class, right? V2 is anti-DOM color class. What about this vertex? What about this vertex? So for this vertex, does not possess a anti-DOM color class, and therefore this is not a global dominator coloring. Am I right? This vertex does not have anti-DOM color class, because this vertex is adjacent to a vertex in the color class 3 and also a vertex in the color class 2. So this vertex has an anti-DOM color class, both DOM color class as well as anti-DOM color class, but this vertex has DOM color class but has no anti-DOM color class. Therefore, this vertex has no anti-DOM color class. Therefore, this is not a global dominator coloring. But you see, I give one more additional color with 4 colors. Now this is a global dominator coloring. For example, see, for this vertex V4 is anti-DOM color class, because this vertex is not adjacent to any of the vertices in the color class 4. For this vertex 2, 3, color class 3 is anti-DOM color class. Okay, and for this vertex 2 is anti-DOM color class for all these vertices, and for all these vertices 1 is anti-DOM color class. Obviously, this is a dominator coloring. Therefore, here every vertex has both DOM color class as well as anti-DOM color class. Therefore, this is a global dominator coloring. So this is a coloring but not dominator. This is a dominator but not global dominator. But this is a global dominator. Therefore, for this graph, chi equal to 2, chi d equal to 3, and chi gd equal to 4. Chi gd equal to 4. Right? So these are some very interesting results have been proved. For disconnected graphs, chi d is same as chi gd, and for connected graph, chi gd is at least 4, and some sort of interpolation theorem. And this is a connection. Now chi is less than or equal to chi d. Because every global dominator coloring is also a dominator coloring, because global dominator coloring requires two conditions. One is it should have a dom color class. That is the condition for a dominator coloring. In addition to that, it also requires every vertex must have a anti-dom color class. Therefore, global dominator coloring is also a dominator coloring, and therefore chi d is less than or equal to chi gd, and also chi is less than or equal to chi d. Okay, and several results combining these inequality, these three parameters have been obtained. And for double stars, we have just observed 2, 3, 4. And as we already observed, asked, are there any graphs for which all these are equal? No, no. So there cannot be a graph for which chi equal to chi gd, and therefore chi gd is at least chi plus 1, and maximum chi plus gamma g. It's very nice setup. You see, chi gd is ranging from chi plus 1 to gamma g. So what's the difference? Gamma g only. So difference between chi gd and chi is only gamma g maximum. And this is a nice setup. See, now we already observed, no, chi less than or equal to chi gamma less than or equal to chi d. We already observed. Now in this chain, now one more parameters come, chi g d. So we, like a dominating chain of 6 parameters, we could have a coloring and domination chain with 4 parameters: chi less than or equal to chi gamma, less than or equal to chi d, less than or equal to chi g. You see, we could set up a new chain of inequalities of parameters which are interrelated by both domination and coloring. So and we have introduced 2 more parameters with my co-authors, and we have set up a chain of parameters with 6 parameters. There are 6 parameters. So by introducing 2 more coloring domination parameters, we have extended this existing chain. So we can call it as coloring domination coloring chain. We can call it as domination coloring chain of 6 parameters, like a domination chain of 6 parameters. So these are some directions for further research. Structural characterization of graphs for which chi gamma equal to chi gamma, chi plus gamma minus 1, and so on. And I can share this PPT to the organizer, where these researchers can see the further directions. So one thesis on gamma coloring, one thesis on global dominator coloring have been published, right? And several theses can be written. Research, a beautiful research is possible on these 2 parameters. Now, see, only one thing I would like to insist upon. See, this is the important aspect. See, what is a gamma coloring? Gamma coloring means a coloring which admits a dominating set, right? Colorful dominating set. But there are several variations of dominating sets are possible. Connected dominating set, total dominating set, isolated dominating set, right? Independent dominating sets. So now imposing the condition on dominating, you can have varieties of gamma coloring. For example, if you ask the colorful dom set to be colorful total dom set, then we can have a total gamma coloring. If you demand the dominating set to be independent or isolate, you can have isolate gamma coloring. So therefore, the avenues are more for further research on this topic. So I stop here. Hope I have reached the audience with 2 parameters, 2 concepts which interrelating for the domination and the coloring. If any questions, I'm very happy to answer.
Thank you so much, Professor Ismail, for your nice presentation. Very good relationship between domination number and coloring theory. Very good. I have just one question. You the chi of G is less than or equal to gamma chromatic number, and the gamma chromatic number is less than or equal dominator chromatic number.
Yes, sir.
And is there any graph there the difference between chi of D, chi dominated chromatic number, and gamma chromatic number be very large? The
Yes, sir.
difference
Yes.
between
Yeah. Sir, I understand now. The difference between chi gamma and chi can be made arbitrarily large.
arbitrarily large, yes.
Not only that, we have proved a stronger result than that. In fact, for a given integers a, b, c, it can assume any value.
Oh,
So
okay.
you can make the difference large, not only large, but also it can be made large as you wish. So it can assuming any value, you can make it very large. The difference can be made large.
Okay.
So
Okay,
that kind
very-
of results have also been proved in the thesis.
Oh, very good, very good. Very nice result. If is there any question, please raise hand.
Any questions? I am very happy to answer.
Okay, thank you, Professor. You are a very good teacher, I think, Ismail. Very good. Thank you so much for your nice presentation. And let's thank again Professor Ismail again.
Thank you.
Thank you so much.
Thank you, sir. Thank you so much for the opportunity. First, I should thank you for the initiative. So I am very, I will always be with you. Whenever you take initiatives of this kind, kindly invite me.
Thank you very much for your nice presentation.
Okay. Thank you,
Wish you
Hamid.
all the best.
Thank you so much.
Okay.